Recording.
Yes, I can.
No,
Stop
you may
my
not.
recording.
Okay.
Yeah, I'll have
So that everybody now know everything.
here. I came here 2 years ago with the goal of hoping to engage myself with the more fundamental questions of neuroscience and as well as computational frameworks. With the IARPA project, which unfortunately ended a few days ago, briefly, but we're still hopeful to apply to other funding resources. I'm going to present today only a glimpse of what we have done, actually. So we've done maybe a myriad of, because every time we gathered to talk about this project, there have been always like interesting ideas, and we had the freedom to talk about these ideas and also implement some of them. And it has been quite rich for me as well, being part of such enriching conversations. So I'm going to only present a small bit of this of these works that we have done. But before that, perhaps I can just make you remember, those of you who attended this meeting. It was 2022, 22nd of April. I was in Turkey, and I was invited to this little meeting with the IARPA. And of course, we have different members of the team, but these four of them inside that red rectangle still stayed on in the Briar project, where we had also, of course, other members now get in. For example, Joydeep and also Chitan, Matt. But it has been an incredible ride for me just to meet these people, as well as the ones who have helped us later on in the project. This is the university that I'm going to be joining. It's in Istanbul, and it's also where I graduated from. It's called Boğaziçi University. It's also Bosphorus University. It's basically right next to the Bosphorus. Istanbul has an incredible view. And also it's one of the top institutions in Turkey. This was actually established as a Robert College by United States.
And what college?
Robert College. It's the 18th century, I think 1863, the university is established as a college and called Robert College by United States. And then they changed the name to Boğaziçi University, I think 1920s sometime. So the language of instruction is English, and it's research-oriented, more research-oriented institution, and it's a government institute, so it's got abundant of resources for research. So I'm really excited to become part of that university in the coming days, but hopefully also keep my relationship with this incredible group of people to conduct more fundamental research in the coming years. So this is probably one of those slides Pawan prepared. Basically saying modern phase recognition systems seem to have exceeded humans. It was all over the place in the media. As you can see, some of them, the snapshots from the magazine saying algorithms that see better than humans, and this is how facial recognition works, et cetera, et cetera. And then we basically start questioning it, like, what is it really true? Or there is some room, like under what circumstances this is true, if that's true, et cetera, et cetera. So the Briar project was about recognizing people from a distance. Under severe environmental conditions such as atmospheric turbulence, because distance obviously leads to blurry image viewing, and this is how our human optical system works due to optical operations, or the small sized faces, for example. When you try to enlarge them, due to that processing, it will cause lots of blur to that face, and etc. So, of course, it depends on what you're looking at. This visual search is an interesting topic as well. Humans are really good at. But our project was more about identification of persons or individuals in a very crowded scene. But if you look at this one, for example, it would be easier to recognize, who's happy in this picture, right? So those types of questions, I think, important to they are very important to the objectives of the project, which is identification of an individual at a distance, because we know that the neural networks, the computational frameworks, are pretty bad at in adversarial scenarios, such as the distance is one of these dimensions where neural networks fail to satisfy certain satisfactory, let's say, performance, because they're not trained that way. So we are interested in understanding the neuroscience or effect of neuroscience or the existence of neuroscience in helping us understand what might be a source of inspiration for designing neural networks that can perhaps behave similar to humans, and therefore perhaps we can expect some robustness in their categorization performance. So this cycle, probably called a life cycle, it starts from testing machine vision systems, like at the very top, and identify their vulnerabilities. Once you test the machine systems, then you go back and test humans in the same settings, right? Then we have to talk about what does it mean to compare humans and machines, and that lead to another whole another research by making sure, for example, machines and humans use the same frontend. I'm going to come to discuss that, but it's not the main theme of today's conversation, of today's talk. But that was part of the project as well. After testing humans in those settings, then we ask the question, do humans perform better than machines? If the answer to that question is no, then we can go ahead and try ad hoc approaches to improve machine vision systems. That's what the computer vision community currently doing. They don't necessarily believe intelligence, in humans is the ultimate one, and therefore they try other ad hoc approaches to understand if humans, for example, if humans' performance can be beaten through these approaches. But if the question is if the answer to that question is yes, then we have to go back and understand how humans achieve their superior performance, and then we need to translate insights from the human vision to machine vision, and then we basically complete the cycle and test the machine visions if that helped in various categorization tasks. So there are three basic overarching umbrella terms here. I just put out here: computational physics and psychophysics. I'm going to focus on today the psychophysics, the EEG in particular, and also some translation work I have done to computational side. Because as I said before, there are many things there are many branches that the project led to later on in our progression. But I want to just only emphasize some of the works that we have done in the psychophysics and some of the translation work in the computational domain. But before that, I'd like to just show you one online study that we run. We asked the participants to recognize the personality, which is as part of that query image. And then we asked them to tell us which one of these individuals in the gallery images that person is. And we run about, I think, 800 participants in that online work. And then that lead to, of course, a comparison between humans and machines, because we were also able to run some machines off the shelf, machines meaning that neural network models, off the shelf, pre-trained networks, and we run them on these images. They're face trained, like face, they know what the face is because they're trained particularly with the face data sets. But this is one of the results Pawan was referring to earlier, which basically shows you accuracy result in different pitch and yaw values. As you can see, that the face could be seen in different directions. There are, I think we use pitch and yaw to characterize that. And then you can see we also shown the performance as a function of distance. When you have 2 and 5 meters, it's pretty close, up close imaging, and therefore you would expect a good performance by both humans and CNNs. but it also is a function of yaw and pitch values. The networks that we used are basically listed in that table, and what you're seeing on the right is the average performance of these networks. So as you can see, and as Alan emphasized earlier, there is a huge difference between the humans and the machine learning models, which are trained on faces. Of course, this journey had started to find an equal platform where we can compare humans versus machines. And that required to understand first how human vision handles or recognizes faces as a function of viewing distance. And this is one of those papers published earlier, which explored yes. Yeah. So they asked the following question: how well do humans recognize faces as a function of viewing distance? And they collected that data to show the functional relationship between the viewing distance, the physical distance, and the proportion of individuals recognized. And they come up with this interesting plot where you can see the whole head is basically giving you the best performance. But if you basically dissect this internal features and external features, you will realize there's a superadditivity in the performance between the internal and external features versus the whole head. This was an interesting finding because that basically inspired us to ask the evaluation problem. Question was, how can we use these results as a benchmark for evaluating the performance of a computer vision system, which led us to think about these computational models and their missing aspects of time and space. So as you know, some of you may know, but that these neural networks do not have concepts of time and space. Perhaps you can reduce time and space into simpler fabric to enforce those space and time dimensions onto a neural network. But I'm going to address the time component, particularly in this talk. But the space component was more about understanding the three-dimensional environment, and one particular interesting aspect of that three-dimensional environment was to understand the depth, in other words, the distance, and the image, that three-dimensional object or three-dimensional face creates the projection on the retina, and therefore by moving around the object, we basically have these copies of this projection in a certain temporal order to be able to capture what we are seeing and establish the perception of that object or face. So to be able to do that, we need to understand the peculiarities of the retina, like for example, cons and rods distribution, acuity distribution function on the retina. So therefore, we can perhaps characterize the effective resolution that we're able to see at a given distance to perhaps fill the gap between the neural networks that has these input images, and therefore that gap between the neural networks, what they're seeing as a full resolution image, versus humans that they use their front-end optics to be able to capture information from a three-dimensional world. So to be able to fill that gap, we need to understand how the distance translates into effective resolution, so we can perhaps use some degradation techniques like Gaussian filtering, etc., to make sure that effective resolution is available to neural networks. So this translation has ended up, so I'm going to basically skip all these ones, but that led to a relationship between distance and effective resolution. We also did some theoretical work as well, but I want you to focus on the yellow squares, but that's the data. And that data basically told us what the precise relationship between the physical distance and the effective resolution. So once you know the effective resolution, then you can degrade your image based on that effective resolution and then feed it into a neural network and then say that, okay, neural network is able to secure specific accuracy at that particular effective resolution or at that particular physical distance. So I'm going to just show you some example of a CNN with a human frontend as a function of physical distance, where you see x-axis is the physical distance in feet, whereas the y-axis is the top one accuracy of some data set. I don't remember what the data set was. I think Spartan, I believe. But so this was about the humans, comparing humans versus neural networks by understanding that this three-dimensional world and the image that subtends on the retina and its projection, and how degraded that projection is based on a distance, we can use that information to simulate neural networks, and then understand their performance, given that we use human frontend for them. Of course, more important question, and which will be the main chunk of the conversation today, is to understand how human brain mechanisms with this available input resolution, they perform better than machines maybe state-of-the-art models. So we need to understand that, and we used, of course, brain imaging experiments. Particularly, we focused on electroencephalography to understand these human brain mechanisms.
So Suayb, when you talk about that, so is this the first time that this mapping between viewing distance is not a set of equations?
It's the best version of this.
Is this the first time that this mapping between viewing distance and effective resolution has been made?
I've never seen any study that is focused on, because some people are interested more in like comparing humans and machines by just assuming that the machines have their own front end and humans have their own, and then just compare them, whatever they have, right? But I disagreed with them because if the front ends are different, then you have access to really high resolution. Then in that case, the comparison might not be apples to apples. But the second reason I'm more interested, or maybe that would help me to advocate where my standing is that the physical distance has more meaning than just a simple comparison between humans and machines. Part of the reason is that humans, for example, develop these excellent learning abilities in this three-dimensional world, and they also associate the size of objects with the intrinsic features of those objects. So there is an association between the size and the intrinsic features of objects. So therefore, when brain does that association, it helps the brain to become really robust. If you compare, for example, a toy train or a real train, then the distance is the only metric that will differentiate the two. So therefore, if you would like to add additional layer of robustness to a neural network mechanism, perhaps you should also make sure that neural networks have the ability to create such associations.
So would you predict that if you took a face that was smaller, as if it were further, but put into a context, maybe using 3D or maybe just using the environment, that makes it appear much, much closer where it should have been larger, do you think that would interrupt facial recognition? You follow my question?
Trying to process.
Yeah, I can
Giving the face
rephrase it.
context, pretty much like giving the face context and giving it, like putting the background back so that it can.
What if you kind of disconnected the context? So I think what you were saying is that the brain is being robust to, let's say, the size or the effective resolution of the face, because it recognizes in the context how far away that face is. Right? If that face were then perceived to be closer, but still that same effective resolution, would that mess up the recognition process?
Yeah, so I think we also have done some experiments here. You can see that adjustment of input size or upscaling, and some of the preliminary investigations suggested that CNNs perform significantly better with the upscaled versions of images using simple, for example, icubic scaling or nose resolution, meaning that you have the face like in the middle of a large image, versus that high resolution phase is scaled up. So therefore you need some sort of interpolation that causes degradation to the image. Which one would you prefer? Well, machines seem to prefer the upscaled version rather than the smaller version.
Those are machines trained on a particular size of face.
Yes, yes. Mhm.
And a similar story holds for humans as well.
I believe so, yeah.
If you have a low resolution face, so let's say a 15 by 20 pixel face, you could show that little thumbnail and ask people who that is. Or you could take that 15 by 20 pixel and enlarge it, as Suayb is pointing out, with maybe bicubic interpolation. So you're adding no additional information, but human performance is better with the larger. Mhm.
Mhm.
Yeah, it's not a completely predictable result because one would have thought that since we have been trained on these little images when we are seeing people at a distance, that is what we would be better at. But no, it's the larger image.
You have an explanation for that?
No.
Because we have not run a specific experiment to just test that. Our experiments were more like understanding the effective resolution rather than humans, subjected to recognize human faces by a small side image or versus scale version. We haven't run an experiment, but I think based on the literature, what Pawan is saying is accurate.
Yeah, and I don't know how it necessarily relates, but if you take a mosaic version of it, if you
Mm.
scale it up by creating mosaic.
So Yuri is getting me to point out.
Saying.
Yuri discovered a very interesting illusion or a phenomenon that I still don't have an explanation for. I don't know if you have it. So you have a mosaic version of an image. So essentially the kind of thing that the TV news does when you want to remove the identity of a face. So you break it up into little squares. What Yuri found was that if you now overlay a grid of lines on this, so you have this collection of little squares that make it hard to recognize what face that is. But you simply overlay a bunch of lines on this. So you're adding no information. In fact, you're adding perhaps distracting information. That overlay of lines makes it easier to recognize.
So there's one other thing to it. So yeah, so first of all, if you take a mosaic image and shrink it down, right, then it's actually, in that case, easier to recognize. Right? If you bring it back to mosaic, it's harder, so the well-known effect. If Pawan is saying if you put a grid on top of it, it makes it easier. However, if that grid aligns with the grid of the mosaic, it's just as hard as it was before.
What made you
Misalignment.
want to put a grid on it?
I had a theory, believe it or not, because I was trying to get at the, what was that, the theory? Who are those guys that? They were like, is it high frequencies or low frequencies? What is responsible for the mosaic effect, right? There was that debate about what was what. So I was trying to get into that and trying to figure out which one it is. So I was playing around with Gaussians and whatever, and then I thought, well, what if we kind of just play around with the grid effect, these sort of weird non-high frequency, not low frequency, but kind of it goes mid frequency, whatever it turns out to be, just these kind of artificial square wavy sort of things. What does that do? And I put it on the screen, and I was like, wow, that took away the mosaic effect. And then I moved it around to be coincident. I thought, how is it possible if this is helping? It must be just in my imagination. And I made a coincident with the grid, and the mosaic illusion came back. I thought, how is this possible? I'm taking away information, still leaving the distracting information, and yet it's having this effect. So maybe I should come and give that talk. Probably have to PowerPoint around somewhere.
Created quite a bit of excitement in BSS when you gave it.
I was just thinking we should publish that one. Break that record.
Hey, I'm still getting things published and I don't even know that.
I didn't even know it was excellent.
All of our work is so far ahead of its time. Nobody scoops it.
So, yeah, and I even did a moving grid, sorry, to go over this. But I even did a moving grid to see if there was some hysteresis effect. And in fact, you could have it going over and it's visible, visible, visible. And in that brief moment, when it coincides with the grid, all of a sudden you can't recognize it anymore. In the very next moment, you can see it again. So
Cool. Cool.
it was fun.
I'm gonna have to pay.
Yeah. Yeah, I was thinking about making a physical version of it. It's kind of toy.
Mhm. Yeah. Toy.
Yeah.
So for $50, get this.
Endless.
Good luck.
We will buy one.
Yeah, I got at least one customer. So what's the point?
We distracted you, sorry.
Connection.
No, I will also forget what.
But I think I was asking, I don't remember I actually asked this. So in what you're doing, so forget about what humans do, and we know there's this distraction, but the neural networks don't necessarily have all this learning that we do. By scaling it up with Gaussians, you can get it to, I guess what you're getting to is that you can get it to perform better
Yeah,
on these small images.
right.
If you had scaled it up with as a mosaic,
I haven't done that. Yeah, I don't know. Perhaps they would probably be as bad as humans. I mean, machines.
Yeah.
But I haven't done that yet. So good experiment. Yeah.
I mean, for the training.
Have you run the experiment? I think you run this experiment. You were just having this grid based
Yeah.
on this on humans. Have you also run them on machines too?
Yeah.
No. Okay.
Yeah, that was done.
All right.
She's like, phew, something else to research.
Yeah, this life was beginning to be meaningless.
Okay, so we were trying to understand the brain mechanisms. So I looked it up in the internet, of course, get some research on what people have done, and particularly maybe more broader mechanism in the human brain is the network modularity. In other words, that's the degree to which functional brain networks are divided into these subnetworks and they're specialized for performing specific tasks. It could be beneficial, like having a modularity could be very beneficial for developing a robust brain, particularly for internal and external perturbations. But it is the individual variability across different humans shows that modular organization is required for robustness of persistent activity perturbations. Modularity does not typically form in computational models with standard training and architectural designs. Okay, this I believe or hypothesize that it could be due to constraints of the hardware, which means the architectural design need to be changed to allow such modularity. But there are also some work in the literature. They suggest that if you change the training, perhaps, for example, one of the training mechanisms that the lab is heavily doing is biomimetic training, for example, that could perhaps lead to some sort of modularity in the brain. And then you can probably say why modularity might be important for robust categorization, because if you've got these modular regions of the brain, then if you happen to have an adversarial example or noise, for example, then one part of the brain could be activated, versus the other could be just deactivated, and therefore you can have these different regions basically working together to accomplish a task. But then the question is, how about we enforce these modularity through architectural changes? That's one of the questions, in our trajectory or path to creating models that can incorporate some of the findings from electrophysiology. And this dimension we thought might be spatial frequency processing, because the earlier literature already established that there are different pathways in the brain that allows us to do this modular processing. more specifically, spatial frequency processing. So the objective is then we focused on spatial frequency processing, and then the literature seemed to argue that there's a coarse-defined ordering in the brain. In other words, it proposes that the coarse information, like blurry image, for example, carried by the low spatial frequencies of the visual input, and that would guide later on in the brain the integration of finer, high spatial frequency details. So this image is from that paper, and this sentence is from that paper as well. It says, initial encoding of low spatial frequency information in faces may undergo refinement through recurrent top-down processing, which results in improved and robust recognition performance. You can also see this coarse-defined processing, this phenomena, not just in humans, but also in macaque and macaque brain and mouse brain. As you can see, for example, for those plots, the blue and the black ones are low spatial frequency, the spike rates or density, versus the red ones are for high spatial frequencies. Even like in the lower levels of the visual system, like V1, but also as you go up in the hierarchy, you can still see this coarse-defined processing order in the V4 renewables. So then we tried to explore the time component.
Can you go back to the slide? I just want to see. So the high spatial frequencies have they happen later, but that's what this is.
Yes, exactly. The time, so this recording has a temporal direction, so therefore the activations start later for high spatial frequency stimuli for the macaque and mouse brain, which are represented by these red curves.
I would guess that high frequency would cause a quicker response, sharper response.
We'll come to that, yeah. I had some findings that suggest that high spatial frequency might be processed earlier than there's going to be alternation, like then the low spatial frequencies start leading high spatial frequency. That's what I found through my EEG experiments. But this seemed to be the dominant view in the literature in the macaque and mouse brains. As I said, I would like to explore the time direction, but the time is more, I think, applicable to human brain, but maybe less to neural network models, because these models do not have time component integrated in their design from the beginning. So the first, for example, appearances of neural networks such as AlexNet do not have any time component in their design. So therefore, perhaps we can loosen the definition of time and then turn it into an order of processing rather than the continuum. So if you look at the brain, you will realize that, and if you think about these rapid or slower spatial frequency processing in different pathways, you can have like arguments such as, oh, rapid LSF processing is basically due to magnocellular pathways because they are myelinated, and parvocellular pathways less myelinated, and also like color could be carried through parvocellular pathways, whereas black and white or grayscale is magnocellular because their connections to V1, the number of connections you have, for instance, are larger in magno versus parvo. So therefore, you have got more pooling. Therefore, you have blurry, data or information, like low spatial frequencies. So the physiology seemed to suggest that rapid LSF, the low spatial frequency processing, would be carried through magnocellular pathways, and slower high spatial frequency processing take place in parvocellular pathways. The concept of order in which these events occur is more basic than the concept of time, as I said before. So therefore, we can consider the total ordering of events in a single process, which would be consistent with our experience of time.
Did you find something with the myelination differences in the Magno versus Parvo, or is that like a hypothesis?
It's what I see. I think I've read a couple of papers that they seem to suggest that magnocellular pathways have more myelin, and that they believe that myelination actually leads to rapid information processing.
Yeah, if you could send some of those references.
Of course, yeah, of course.
Is there any component of, from the information perspective, so lower spatial frequencies, you have less information to compute with. In higher spatial, you've got more information. I'm just guessing, but maybe there are more layers, or you need to involve more neurons in order to process that.
Yeah.
Is there anything around that, like larger areas need to be processed one pathway versus the other?
No, I think it's a good point. I can't remember if the papers are necessarily referring to your argument, and yeah, this could be due to that too as well. But I don't know. No.
Oh, very good.
I was gonna ask if you could go back to the slide one more time. Just want to look at this. Just the clustering is kind of interesting. It's like a discrete jump in the nosphilon neurons when you go from the low spatial frequency to high spatial frequency. So all the low spatial frequency ones are right on top of each other, and then there's a sudden jump when you go from 0.10 cycles per degree to 0.24, and it shifts.
It's not.
It seems so continuous.
Although there is more of a jump from
But there is a
1
jump.
to 0.24.
Yeah, there's a jump in the numbers as well, like
Sorry.
4, 8, 10,
Oh, yeah,
then
right.
24. So
It's maybe a little sleepy, but they still seem okay. Anyways, it's curious.
Alright.
Because then that kind of says this goes Magno, this goes Parvo. Yeah, all the high spatial frequencies go down one channel, all the low spatial frequencies go down another
Oh, yeah.
channel. But that seems,
And the threshold is somewhere between those two groups.
That'd be
yeah,
interesting if there was a stark difference in threshold,
that would be surprising.
but possible.
Maybe.
It's possible, not necessarily probable.
So we can see that Marin and Lucas have been looking at what might be the genesis of the Parvo and Magno distinction. So we know that these screens exist, but why do they exist? So they are taking the standpoint that maybe there is some developmental root to this. So the gist of the story is that developmentally, we start out with poor acuity and poor color vision because of the immature cone system. And then over time, our acuity improves and our color perception also improves. So could it just be this temporal coincidence of poor acuity and poor color vision early on in the initial months of life? So the receptive fields that are being birthed at that time, they just come to encode these two aspects of the visual imagery: low resolution, low chromaticity. And later on in time, when the animal or the human has higher resolution and higher chromatic sensitivity, the receptive fields that come online at that time have those properties. And this confluence of low res, low color versus high res, high color, this is one of the defining features of the Parvo versus Magno distinction. So the reason why we have these two streams might lie in the developmental histories that we go through. But it still doesn't explain if there are myelination differences between the two streams.
So I ask, I mean, you seem to suggest, or maybe I'm wrong, that it's strictly a developmental necessity that you have this low resolution, a low color condition. And then there's advancement, developmental, advancement by which you gain the higher. Is there any evidence for, a learning advantage with regard to starting out low?
Yeah.
Low
so-
resolution. And
So
well, the last part of the sentence was just an advantage whereby perhaps, that the fine resolution actually maps onto and and maybe not just at the time of learning, but forever. And it maps onto the low in a way that essentially creates like a two-channel function where they're mutually beneficial and complementary. I don't know, just something I was thinking about.
So I don't know what the answer to the second question is, but for the first question, Lucas or Marin, do you want to respond to that? With the benefit that you find in having the magnet system?
Yeah, so so in this specific study, so we looked at the dimension of color and we looked at the dimension of acuity. And generally the story seems to hold that starting with having very little of this and then later on having more of this seems to be beneficial, so that the network or the human or whatever species also has this, that they focus on the big picture essentially, and that they don't get distracted either by the high frequency noise or details or by specific color alignment. So I think the story generally seems to hold. And then in addition, there's now this consideration of this correlation between these two properties and how that could explain these pathways. But I also don't know the answer to the other question you had, whether these two streams and how they exactly interact.
Yeah, it seems like the two streams have, they're not like the low acuity stream doesn't just turn into the high acuity stream. It's like they have this, just my intuition, that they have different functions, almost like two ways of seeing that support each other. That's just kind of intuition.
Yeah.
Future research.
Yeah.
So, is the argument that evolution set up these two streams because of this progression? Or is it more these two streams are set up by development? So initial low acuity vision brings on the one stream, and then later on the other one turns on because of the high acuity.
Yes, it's the latter.
The latter.
That there is a certain kind of developmental progression in the front end, and that forces the back end to develop these two things.
But is there still, sorry, is there still a question? Did evolution choose that because it works better? Or,
Do you want to?
Is that what you're getting at?
So
Just wanted to know.
Yeah, oh, yes.
but they're both there initially, right? The two streams.
The part
Initially,
so Magno is has a temporal precedence
okay. Okay, that's the. And
in development.
by how much?
I don't-
Well, when we were looking at the neuroplasticity chart the other day, all the vision was done
Yeah.
by like month 11 or something like that,
Mm.
for the age for humans. So I would assume that the parvo has to be developed in that process, in that time frame.
Yeah. So, right, so in terms of, if you look at the acuity progression, within the first like 5 or 6 months, a baby's acuity is already much better than what they start out with. So it's quite possible that the Magno stream has a precedence of a few months, like 3 or 4 months, before the parvo stream begins.
I'm just thinking, have people done this in mice or something, where you can just chop the or in macaque, developing macaque brain, you can, because they actually have nice layers of the magna parvo. So then you could maybe see that initially you only have like you don't have a striped LGM. Essentially, you have just the magna system, and then the parvo stripes develop between them, or are they?
So the Magno and parvo distinction in the LGN is the upper layers are all parvo, the lower layers. Are
Oh,
all,
sorry, yeah, I mixed that up. Yeah,
It would
you're
be
right.
interesting if you cut out the magno, like if you were, as you were saying,
Mhm.
if parvo is faster to develop, and if it's, I mean, if there are a lot of developmental delays or not. So,
If a human is blind up until say 11 months.
Yeah.
Has magna parvo already developed, or?
Was it?
hello,
or is
How
it-
are you?
sorry.
How are you?
That's Daddy.
We don't know.
I'm well, thank you. I'm listening to an lecture.
There's also, there's a delay in input,
Mhm.
because of your uptake based on time, so.
Yeah.
You know, is there, do we know that it is development of the?
Yeah, or if there's some kind of a genetic programming that even without this developmental progression in the front end, you would have this distinction in the two screens.
Right.
Yeah, yeah. I don't know whether so nothing in my reading has yielded any evidence. But that would be a great animal study to do. Yeah.
Can I ask, how do we know that the stream develops later if the front end cannot detect it?
Yeah.
So you wouldn't expect to have activation there because that information is not being received. So the non-activation of that stream might just be because the front end is not passing that information. But the stream might still be there. That's what I missed.
I think it's similar, yeah, it's along the same lines, yeah. So that, how can you tell that trying to say again, parvo is
The
not?
parvo stream
Yeah.
develops later.
Yeah.
If the front end simply cannot signal.
Yeah.
The parvo. So
I think there's a lot more research coming out on some of this because at least occupational therapists at this point are recommending that newborns up until about 6 months are shown black and white flashcards and it helps with their development. Now, I don't know too much about that, but I think that there's obviously science behind it if they're recommending it. I haven't looked into it, but I know that that's the recommendation for upcoming parents. So. Little flashcards, I was like, okay, I can just go and get like 2 + 2 flashcards and get math at the same time. But no, I know that that's one thing that people are now doing is, you know, any sort of time that the baby's awake, because baby's awake only a few hours a day, they're using flashcards as a part of that to help, you know, the vision develop supposedly. So I don't know why and what the research is behind it, but.
But I would be very interested in learning what are the kinds of things that have been recommended for young.
Well, I can sing all of Facebook posts I get.
And if Beethoven is playing while you're doing the flashcard, it's even.
Yeah, good question. So what I was going to say was there's probably somewhat of a staggering in time. So the front end, let's say, is able to signal spatial frequencies higher than a certain level by, say, month 6. If you find that the parvo system does not come online until month 8, then you have a reason to believe that maybe it's causal, that
It's lagging behind.
only after the front end is capable of signaling those, then you get responses in the back end. The tricky question that I think you're raising is prior to that, to the front end being able to signal the high frequency, how can you possibly test the back end?
Yeah. Unless you do, I think that's maybe what you said, if you, in another species, if you can damage that region and see it never comes on. Or you damage the magnal pathway and see if some, that.
Or if you raise an animal blind and then give them poor acuity for a few months versus giving them high acuity right from the beginning.
Or in Prakash children, right?
So that's I think that's the way. So if this animal, after having been raised blind for the first 6 months, so now the front end has matured during those 6 months.
Start at the same time.
Yeah, so now they are starting with the front end that can signal both low and high spatial frequencies. Would they still show this staggering of the development of magnal and parvo streams, or would they now show that both magnal and parvo streams develop at the same time?
So is there any evidence from the Prakash children? Because that would be basically that
No, so
kind
we
of.
haven't been able to, I mean, we can't image the magnal versus parvo streams. Sure.
Do you ever get this urge just to like go and open a mouse lab and then you know actually cut open the brain? And maybe they did a little bit.
Well, the guys did the chicken studies with the ping pong balls.
the New College.
Was it there? No. You guys still around?
So there are quite a few people like Nico who are doing with chicken,
Oh,
with
okay.
chickens.
Yeah.
Mhm.
Interesting collaboration.
Great.
You
Yeah.
can invite one of them.
Bite one of them?
Invite.
That's the communication.
Strange kind of collaboration.
Yeah.
I thought you were the chicken. You were talking about research.
Sorry, sure.
I'm good.
Yes.
Those are all interesting.
I'll just
questions.
go one more
One more
question.
question, I'm sorry.
Yeah.
But tracing back to the retina and the midget and the parasol cells,
Mhm.
do you see that you have some delay, like the parasol cells, which corresponds to the magnet system, develop earlier? Or
So that's a great question. In fact, the paper that I was mentioning, that Marin have worked on, that got turned down from PNAS just because one of the editors raised the point that, oh, we know that it's all due to the retina. And I don't think that's known whether the time course of development of the midget and parasol system, whether they both come online at the same time. But
Somebody knows.
I'm sure that, yeah, I'd be curious to see if there's some books.
yeah, I mean,
development of the
that
retina.
question is unknown. The second one is, what is the consequence of deprivation? So if you have, say, a Prakash kid, would the proportion of midget and parasol cells and the sizes of the receptive fields, would they essentially be the same as the distribution in the normally sighted?
That's what I was curious about. Maybe there's a dendritic protein process in the
Yeah,
retina.
one would expect that there should be some activity dependent impact on the sizes of the ganglion cell receptive fields.
Any more questions? Yeah, so we asked all the questions. I think I need to stop here or something. So anyway, I'm gonna probably have to skip some of these slides because so anyway, so let me tell you what I have done perhaps to understand what's happening inside neural networks. Because as I said before, there's no time, but perhaps there's a processing order. So I thought that maybe it's reasonable to define the processing order of events like LSF and HSF processing. And then the question is, the similar processing order observable in neural nets, such as we observe in the humans, the biological systems? And if so, what does that imply? So I took this one of these well-known models, VGG16 architecture, which is trained on VGG face, and I use another data set where you have close-up faces as my inference to use my inference time. And I basically divided the image domain into high and low spatial frequencies and the full resolution, and I put them through the network and then compare the convolutional layers using some sort of structural similarity index. So these feature maps you see on the right, they're basically compared based on certain structural similarity, or activations are compared using some sort of structural similarity. And that lead to SSIM score on the y-axis and the x-axis, the layers, showing you how the low and high spatial frequency similarities, like full resolution versus low spatial frequency, or full resolution versus high spatial frequency. These feature maps are compared. And what you're seeing here is that as you move on from the beginning, like in the very early stages of the network and towards the end of the network, for different sigma values, we kind of see that the network is preferring low spatial frequencies in the early stages of the processing, and then later on, high spatial frequency is prioritized or preferred by the neural network. So, which we thought perhaps is in line with what we have seen in the human studies, electrophysiological studies for the macaque or humans. But then the hypothesis is like networks having this property perhaps tend to perform better for long range and distance identification tasks. I've run the same study for the ResNet 50 architecture. But then I failed to see the same sort of trend. And that was a bit depressing for me. Again, it's the same, different architecture, but the same data set.
The perfect slide to close on. And that was a bit.
It was a bit, yeah. I was a bit sad. Although this analysis was simple. So that's the end of the story. It's just that they don't conform to what we observe from human studies. So, but
Sorry, can I, it sounds like you're saying something really kind of fundamentally interesting about the network. So the SSIM, you're talking about the structural similarity of the network architecture or
no, the activations, the feature maps that generated in each convolution layer in the inference time. So if you put the image, for example, I'll go through all these, weights and etc. Then you have some information that's passed to the next layer, right? So that's the information that I'm talking about. That's the feature map that basically evolves over time.
Mm-hmm. Do you know, can you say in any way how this architecture is different from the other architecture?
So yeah, so this architecture is feed-forward architecture. There are no extra branches that connects different blocks or processing blocks, I would say. But ResNet is an architecture that has got specific identity branches, which connects, for example, earlier blocks to later blocks by a simple identity information transfer to help, because these networks are trained using backpropagation algorithm. So therefore, in order to not to lose the gradients, because the gradients could be really small. So by using these, long range branching, you can basically help the optimization process. You basically get rid of that vanishing gradient problem through those branches. However, later on in, I think in Pojo Lab, they basically have written a paper saying that the ResNet is more biologically plausible because we have those such connections in brain. And you can also think ResNet, which I'm going to probably show you how the architecture looks like. But ResNet also can be interpreted as a recurrent network that is basically rolled out. In other words, you can think of a recurrence. Basically, if you just roll it out, you will see that there are blocks that are used again and again and again. So in that fashion, ResNet 50 is also some sort of a simulation of a recurrent network, which is what Brain is doing. And I think those two reasons kind of explain why ResNet 50 is outperforming in many ways, or become really popular. I get like 200,000 presentations. Yeah. So this is the performance with this NIF pitch and yaw values in different distances as well, like x-axis is the distance, and the red one is the human, VGG16 is the white, and the ResNet is that pink square with the blue line. And then perhaps what I saw with my simple experiment, I saw that the ResNet 50 seemed to underperform compared to VGG16, and then this could be a small evidence that the VGG16 seemed to have an alignment in terms of the frequency processing, whereas ResNet 50 doesn't have an obvious, alignment with this low and high spatial frequencies.
Does it sound like there's a trade-off between being able to recognize low resolution faces versus like some of those things that on the first slide you showed, being able to recognize faces under the best circumstances?
Yeah, so there might be a trade-off. That's a good point. And but as I said, my claim that a network being able to process low spatial frequency earlier than high spatial frequency might be a reason for a better performance, but it's not probably not the same or the only reason. So which we need to explore perhaps in more detail. And also the way that I measure the prioritization of low and high spatial frequency is also subject to criticism. It's just a simple feature map comparison, which doesn't necessarily tell us which which one of these frequency components are preferred or prioritized in the processing. Anyway, so one of the takeaways from this simple experiment was architectural dependence is obvious. If you choose one architecture, then and also a task and a data set, you will have better or worse performance. But we hypothesize that human robustness might be encoded innately into the substrate, in other words, the hardware structure, because all these networks not necessarily have a hardware similar to brain. There are some similarities, but perhaps we have to improve those similarities. So the explicit tracking schemes needed to deep down the network to understand the spatial frequency preference of the network, and training regimens, for example, that could benefit learning. So initial low spatial and late high spatial frequency exposure. And how does the external stimulation shape architecture, and how do the dynamics of architecture change the requirements of training? So it's not like we have these static architecture and then we change the training regimen. Perhaps we can think of changing the stimulation and then the architectural changes, and then we think about what's next in the training, setup to make sure that architecture, which has changed based on the previous training, is best suited. It's kind of like a feedback mechanism between the training and the architecture. They can kind of evolve over time. So to be able to do that, then you have to integrate architectural changes in the networks. So I'm going to just skip this. What I want to talk about, so those are the papers that I referred earlier. One of basically saying, like, we found that residual learning is residual. When I said identity branches, are they called residual branches, recurrent neural networks, and visual cortex. So therefore, they argue that this ResNet type residual networks can be used, or they're kind of in nice emulation of recurrency and also these long-range residual connections in the network, in the brain. So I thought the ResNet is a good starting point. And I haven't seen with my simple experiment, the ResNet is not conforming to the human's prioritization of spatial high frequencies. So I started with the ResNet. So here are some of the architectural changes I would like to talk about. So I looked at the ResNet, and this is the ResNet on the right. So you can see there are 4 different stem cells, or they call it stem cell, but there are different blocks in those stem cells. The ones that are on the very beginning of each stem is called downsampling. So you basically downsample the image. That's why they call it DS. But then the rest of the blocks are residual. I've got residual connections I call the residual blocks. So what I did, basically, I take up, so I enforced the spatial coupling or decoupling into the network, rather than having a simple branch that connects the input to the next output of the next block. I basically divided it into high and low spatial frequencies, specifically with certain Gaussian filter where this parameter of the Gaussian filter is subject to optimization. Okay. And then I after dividing into 2 different components, spatial frequency components, then I added low spatial frequencies in the same block, and then I forwarded that high spatial frequency for the next block. So the reason you forward high spatial frequency for the next block is that you believe, or like based on previous literature, it seems like the high frequency processing happens later on in the trajectory perception. So you have to make sure that high frequency is available later in the processing order of the network. Okay. So here is, for example, 3 different blocks. The ResNet 50 is on the left. ResNet Bio 50, the biological plausible mod, is on the right. And I have this frequency decoupling, and then there's a fusion in the same block, but also this high frequency is feed forwarded to the next block to be fused again with the residual branch of the next block. Okay. So these 3 different changes made: the frequency decoupling, time lag processing, and fusion. Of course, these 3 different changes led up to introducing different weights into the network. Like, for example, in the fusion, what would be these weights? How much you want low frequency, how much you want high frequency in each block. So those new weights are subject to optimization. But also, I think the most important part of that architecture is that these weights could help you calculate the input agnostic frequency preference of the network. So independent of the input, you can basically use these weights, okay, and the sigma value that is chosen by using Gaussian functions, multiply them or modulate them with these weights, and then sum them together. You will realize that how much low frequency or how much high frequency is preferred or prioritized after optimization by the network. Okay.
Does noising and denoising have any result in any improvement?
In the training?
Yeah.
I didn't, so my training is based on full resolution images, but my tests are based on different noise components, like Gaussian noise, Gaussian blur, and etc. So I haven't introduced noise in the training system or training regimen.
It seems to be helpful.
It could, yeah, it could. Yes, it could. Yes, that's a good point. Yes.
So you train the network from scratch?
From scratch, yes. I also have some pre-trained ResNet, and then I introduced these new weights, and then I also did that too. I've got some results for that too.
Oh,
yes.
And using the same stimuli for training.
Yeah, stimulation could change. I mean, the full resolution. Do you mean
Yeah.
full resolution? Yes, full resolution for all networks. Yes, but the
But
data
I mean, it's the
set changes.
The data set does.
Data set does change. Yes.
Are they comparable results to starting fresh versus adding the bio to the ResNet that you've already processed? Are they comparable results, or is there still some lack there as if if you started with the bio off the
So
top?
it's a good question, and I think I would still have to explore that. But my experiments with the pre-trained ResNet and then to apply those changes was for let's say data set B, and the training from scratch for data set A. So therefore, I'm not using the same stimulation for these two different training schemes. So therefore, I would not be able to answer your question, but it's a good question. I haven't had the time to look into that. That's a good one. So let me just, so there are some properties of the network, like for example, having these low spatial frequency decoupling that can actually act like an anti-aliasing filter. We know that, if you sample images like downsampling, for example, could cause something called aliasing. So the image in the frequency domain images, their frequency responses could basically, the pixels overlap with each other, and that causes image degradation. And that could be happening in ResNet, I believe. So therefore, these LP, this low spatial frequency filtering, could be helping with the aliasing problem. So let me just jump into so this is the more generalized version. So instead of having low and high, but you can actually have multiple frequency components by adding different filters. So you can process, for example, the frequencies between 5 and 10, 10 and 15, or 15 to 20. So you can basically treat each different bands differently in the generalized version. So here, what I was exploring is that I thought maybe the innate characteristics, which could basically lead to these architectural changes. And then I just wanted to test the architecture with varying different test ratios. So if you have a data set, then you divide the data set into two parts, one for training and one for testing. Okay. So if you take most of the people take small portion of that data set for testing and use the rest of the data set for training, just to make sure that training is done well, right? For example, 90% or 80% for training versus 10% or 20% for testing. Here, the test ratio in each one of these plots basically tells you that the percentage of the data set used for testing, okay? So I'm showing you three different accuracy results for ResNet 50 and also the bio version. The bio version is the yellow or orangish color, whereas the ResNet itself is blue and dark blues, under three different degradations. Okay, I use Gaussian noise, which means each pixel is degraded with a specific noise value. The Gaussian blur, so I have a kernel that basically makes it look blurry. And also I have salt and pepper noise. So what you see on the x-axis is that noise level, that parameter, because each one of them has one single parameter. So therefore, if you've got noise level 0.4, that's the sigma value used for Gaussian noise, used for Gaussian blur, and also used for salt and pepper noise. Okay, so that's why you're seeing in 3 different scenarios the performance goes down as you increase that parameter from 0 to 1. Okay, so one of the observations you see is that as you have larger test ratio, 95%, and only have like 5% training, you seem to see that there's a performance, the gap between the gap between the performances of these bio version and the original version seem to increase relative to each other, which might sign that this architectural change could be helping us learning from only a few examples. Okay. This is for fashion eminence, which is grayscale data set. This is CIFAR 100, which is RGB data set. And I also did as I said before, I've got the ResNet, original ResNet, and it just pre-trained with ImageNet. And then I added this extra changes in the network, and then fine-tuned the network with a data set called Army data set, which was provided by our funders, which has got 5 different distances: 2 meter, 5 meter, 300, 650, and 1,000 meter. I used 2 and 5 meter images. These are close-up images, and then blurred them as well with certain sigma range, and then test them on turbulence degraded imagery, which are taken by cameras at 300 millimeters and 650 meters. And as you can see, comparing ResNet 50 and ResNet Bio version, you seem to have a better performance with the biologically plausible model.
You haven't compared to humans additionally with the same data set yet, have you?
I think we have it,
You
right?
have the data.
Oh, you have the data, okay.
You have the data, right? Okay.
Because that would be interesting if you compare like that on all the graphs and everything, just how humans may like compare, to know, can we actually get the data sets to work like a human?
Yeah.
We have data comparing humans to these networks, but not the bio-inspired networks.
Yeah. I'm wondering, like, if we add the bio layer, does it start to emulate humans a lot closer? How far off are we still?
Mhm.
Yeah. Okay.
Not that I want computers to be as good as humans personally.
No,
But
I
we
mean,
replace ourselves.
this was one of the objectives of the Breyer. Actually, IARPA people were interested in comparing humans and machines and make the machines, perform better than us.
You should contact all those news sources from the beginning and say, you guys are totally wrong. Here's my data.
Yeah, right. Anyway, so we also found that these networks, these time lag and also frequency decoupling seem to help us with the heat maps that are more akin to human saliency maps, which we generated through eye tracking device. But if you compare the ResNet and the bio version, you seem to see that this biological plausible model seem to have a more focus on the faces. You also see here, for example, that the ResNet 50 compared to ResNet Bio 50. The Bio 50 seem to have a more focus on the image compared to the ResNet 50. So I think the one question that we would like to explore is that, we understand the performance is better in various different adversarial conditions, but how are we going to interpret these weights that we optimize? These are output of the backpropagation algorithm. Seem to have these sigma values optimized as well as weights. It's kind of hard to understand, which frequency components preferred by the network. So as I said before, if you did some algebra, you will realize that you can use an idea like something like, perhaps I'll just skip this here. So if you take a look, as I described before, if you take these Gaussian functions and then multiply with these weights, the algebra, for example, says, you can see that there's a main branch and there's a residual branch. Residual branch has 2 components now, the low pass frequency and high pass frequency. Use the coefficients for low and high spatial frequency, and then multiply them with these Gaussian functions, then you can actually plot some heat maps, which are shown on the right. So the heat maps seem to suggest that the first stage, I mean the stem cell, basically, the first stem cells seem to prefer high frequency, and then the second stem cell seem to have a transition, and then the third stem cell seem to prefer low spatial frequency, and then the fourth basically is almost zero, as you can see. So this observation basically corroborates the finding, which is not necessarily what we've seen in literature, but what we expected, perhaps some of us probably expected, which is the progression from high to low. Okay, so this I said before, this is independent of the input. I just use these weights and etc., which is part of the architecture. And this seemed to suggest that the high is preferred earlier and then the low preferred later, using these two CIFAR 100 data set with different parameters of the network. So that inspired us to run some sort of, let me just jump to the EEG, because we seem to see the same type of trend with other data sets like CIFAR 10 as well. But we are interested in knowing how the humans preferring or having prioritization spatial frequency components of the stimuli. So we run an EEG with the help of McCall and the design with the POAN. And so we basically had these low and high spatial resolution images for faces and objects, and also full resolution as well. It's a free viewing task, so there is nothing for the subject to complete. There's no task to perform. They basically look at the images for 300 milliseconds, and then there's a break up to 1 to 1.5 seconds, and then they see another image. We use this one back paradigm because if you see an identical image, the same blur and same object, then you have to press a key. That's for attention check. But we don't use the EEG resulting from looking at these images from our analysis, further analysis. So we've got 6 different combinations, like face could be blur, sharp, clear, and object blur, sharp, and clear. And we basically had, I think, how many trials? 40? 100 trials? Yeah, 100 trials for each one of these combinations, right? So 100 trials for each one of these combinations. And also we have, I think, run 10 subjects, but we only use 9. And then we looked at the event-related potentials. And let me show you the final result. This is the average across subjects and across trials. So what you're seeing on the left side, the face and objects are both averaged. The red one is the high spatial frequency in stimuli. Blue is the low spatial frequency stimuli, the ERP waveforms, and the green is the full resolution. So obviously, as you can see, that the HSF, the high spatial frequency response is happening, if you look at the before 200 milliseconds, happening a little earlier than the low spatial frequency, because there's a phase shift because the waveforms look alike, but there's a small phase shift to the left. But if you look at what happens after 200 milliseconds, then you will realize that the low spatial frequency is now prioritized over the high spatial frequency. So there seems to be an alternating preference in the human brain. And we seem to see the same type of trends with faces only and objects only, which are shown on the bottom left. But if you compare, for example, object versus, in the basis of low spatial frequency or high spatial frequency, object versus face, we don't see much of a difference between the two. Only maybe little potentiation differences for face and object. So that's interesting because we didn't expect, we seem to see that the low spatial frequency, in the literature seem to be prioritized, seem to be believed to be prioritized by humans and also mouse and macaques. But in our experiment, we've seen that there's some earlier prioritization for high spatial frequencies. And we also looked at the topo maps, and we also seem to see the same sort of trend, as you can see for the face, for the first 2 rows. You can see that the activation starts in the occipital cortex, and then it moves on to the frontal earlier for the high spatial, which is space sharp means high spatial frequency. And then it stays there longer, whereas the low spatial frequency comes back on the occipital lobe earlier than the high spatial frequency. And we also did some analysis on the hemispheric spatialization. We also have seen that low and high spatial frequencies are differentially processed by the left and high hemispheres and the brain. For instance, as you can see that on the right, I used some metric called residual connectivity strength, which is based on imaginary component of the coherence. What you see on the right is that in the very early stages, the left space, so the top figure is low spatial frequency and the bottom one is the high spatial frequency. So the left on, I'm sorry, the one on the top basically shows you that low and high, left and right hemispheres are involved in processing those spatial frequency in the early stages of the perception. But the bottom plot shows you that the right hemisphere seem to be active for the high spatial frequency earlier, and then the low spatial. Then the left hemisphere takes over and then processes the high spatial frequency later in the perception.
Is that a known effect that the right and left hemispheres process spatial frequencies differently?
It's known in the literature. Yes, it is known in the literature. Yes. Okay, let me just skip that one. Okay, so. There are, of course, I presented this work on VSS, and I've got some feedbacks from various people. They wanted to extend those results to ImageNet, EchoSet, right, ecologically motivated image data set, and etc. And also the indigenous behavioral similarity, which I used frequency preference. But they also said perhaps you can also take a feature map correlations with the baseline, which is kind of maybe the next measure. I also done some mathematical analysis using these continuous interpolation of the proposed discrete models. So the one on the right is the basic ResNet architecture, where you have these the filter that acts upon XN, and you have these branch that's the identity branch or residual branch that carries over the input to the output. So you basically add them to define the next input output in the block. But if you take that extent and throw it to the left, okay, and then divide everything by 1, which is going to be like delta t, you can basically approximate the differentiation operation, right? So therefore, you can have this simple differential equation to describe the behavior of a residual network. And I also run some similar analysis for this new architecture, and it seemed to help me understand the informed selections of parameters, because there are so many parameters and I didn't know how to choose them. You have to basically probably choose lower and higher upper bounds on these parameters. So it basically helped me understand how to choose them. This hemispheric spatialization is, I think, very interesting, and but I always thought about like how can I integrate such an observation in the hemispheric spatialization domain into my network. And somebody also suggested curriculum learning, which they argue that the biomimetic training is a special case of curriculum learning, like start from hard and then go to the easy questions and make it more biological plausible. I want to just maybe emphasize a little bit on the hemispheric spatialization, because that's what we observed already, but I just wanted to map it to these stems on the ResNet. For example, stem 1, both hemispheres prefer low spatial frequency. In the stem 2, perhaps left hemisphere prefers LSF, low spatial frequency, but right hemisphere prefers high spatial frequency. What happens in stem 3? Well, left hemisphere prefers high spatial frequency, but right hemisphere, like kind of, we don't know, maybe none. And then the last one, the stem 4, perhaps left hemisphere prefers high spatial frequency and right hemisphere prefers high spatial frequency, as you can see on the far right. So perhaps these observations can be integrated into the model, because the model allows you to integrate such observations, because you can see that these the number of residual residual connections that you want to make with the downsampling block versus the residual blocks in different stem cells, they can be varied. So, for example, instead of using this sort of thing, the one on the left is the LSF prioritization, like time lag is applied to high spatial frequency component. Maybe you can apply the prioritization to low spatial frequency component. Perhaps you can have this time lag processing applied to low spatial frequency component to prioritize the high spatial frequencies. Okay, so by just changing this branching, you can have low and high spatial frequencies prioritized. And you can see on the left-hand side, the dotted lines for the high spatial frequency, the solid ones are the low spatial frequency. And therefore, you don't need to apply the same type of branching on different cells. Because as you can imagine, ResNet is believed to be a nice approximation to recurrent neural networks. So therefore, every stem can be taught as a time evolution of the same hardware. Okay. But if you change these LSF and HSF prioritization in different cells, that can actually correspond to reality where you have the same hardware changing prioritization. Okay, that's kind of the idea. And you have two of them, as you can see, to simulate the left and right hemispheres, because we know the left and right hemispheres seem to have different preferences for high and low spatial frequencies. Okay, so there are, of course, questions. One of them, as I probably alluded to earlier in my talk, the nature and nurture problem. In other words, the nativism and empiricism. The nativism is more like the architecture, the true hardware substrate, right? So how does that evolve over time? Empirism is more like, it doesn't matter what the architecture is, just focus on the stimulation, right? So I'm trying to understand that this the wiring in the architecture versus the structural changes that are led up by the stimulation. And this relationship could be, it could be easier to analyze such a relationship by changing the architecture by these modifications. And then perhaps you can allow the architecture to change over time in a training progression, right? So perhaps in the first 10 epochs, use a specific architecture by imposing constraints on these weights and etc. But in the next 10 epochs, then you change your constraints.
Are there any dynamic networks like that? Dynamically trained?
I think the most closest one I've seen is the hierarchical neural networks that they have got these interesting low and high future selections that's basically probably changing the kernel size so that they can have these long range dependencies that can be, but that's the closest one. I don't think they're inspired by the human brain. But perhaps there are other studies that I might have missed.
So that's a neat idea.
Yeah. So as I said, training has significant impact on the architectural and structural modularities that develop in the brain, like biological mechanisms that enable modularity. And once such modularity develops, then how does the training proceed? That's kind of the question I might want to address. And of course, the tools to measure this degree of modularity, like we only focused on EEG, but perhaps fMRI and MEG could be useful. But those electrophysiological studies and the tools we have to measure modularity for brain is not necessarily applicable to computational systems. But then how are we going to measure the modularity for computational systems? Perhaps we can use information theory and other type of approaches. So the important for critical this I think modularity identification is very important for critical decision making, particularly for some of the applications where you have like medical decision making or self-driving. That can also help understand the networks, like what their preference in terms of spatial frequency also help us understand how the networks behave. So that can also help the explainable AI. And finally, architectural neural formations eventually lead to changes in perception and interpretation of the external stimulation. So the hypothesis could be if there's a continuous feedback process between external and innate mechanisms, evolving in the internal biological substrate. As we already talked about these biomimetic training, so I also run my network on using the biomimetic training. See if this type of architectural change helps with the training changes. So based on my experiments, so the one on the left is the no biomimetic, the one on the right is the biomimetic training for ResNet 50 under 3 different degradations: Gaussian noise, blue and salt and pepper noise. And the green ones are the biological version. And this is for, I believe, fashion and mist, so you've got only 10 classes. So as you can see that the biomimetic training seemed to help both ResNet 50 and the biological version or the biological plausible version. But I think it's easier to look at this one because this basically uses, groups together the performance results for ResNet 50 and ResNet, the biological plausible version of the ResNet 50, test ratio 20%. But what you're seeing is the green ones are the biomimetic version. The blue ones are the full resolution without this biological biomimetic progression. When I say biomimetic training, I only change the resolution, the acuity, okay, not the color, not anything else that relates to the biomimetic training, just the resolution. And fashion and mist doesn't have color anyway. So what you're seeing here, as you can see, the biomimetic training helps both networks, okay? Like in the ResNet 50, you can see the salt and pepper noise, for instance. The network, the ResNet 50's performance is basically improved for biomimetic versus the full resolution. However, the improvement for the Gaussian noise is not that very visible for the ResNet 50, whereas it is quite visible for the biologically plausible version. Okay. Thank you very much for abrupt answer. Thank you very much for I present this in the VSS and I'm really happy to take any more questions you have. Thank you.
You presented this in a 15-minute time.
This is just a poster, so it allowed me more time. It allowed me to more time. Yes.
Football where the runner with the ball is being shielded from all of the rest of the people who are tackling him by other members of his team. So that's what we had to do. He sure it could be on the podium while the rest of us prevented any other speaker from accessing the podium.
Okay. Very much from leaving the room.
All right. Yes. So if you have any questions or any comments, and also thankful for the members of the same project that helped me, like for example, EEG experiments designed mostly and also conducted by Mikhail and guidance from Pawan and other members of the project. Unfortunately, it's a great pity that the project ended abruptly just a few days ago, and but I'm hoping to get our work published. So.
Yeah. But I don't know if people have tolerance for another question.
Please go ahead.
So going back to your result with the kind of 2 different phase shifts, low and high frequencies. The high came first, early, like before 200 milliseconds, and then the low frequencies.
EEG,
processing
right?
on the EEG.
Yeah.
On the EEG. Yeah.
This one?
Yeah, this one. That's right.
Yes.
Yeah. So, and do you have a hypothesis for that? One hypothesis might be that different types of processing are happening at one time frame versus another time frame. So different inferences are occurring at the 2 different time frames.
So I thought about that, and I think that the high frequency might be preferred by maybe at the very first shot to help us, because the categorization, the perception happens by the end of 200 milliseconds, I would say. Probably you will have a coarse understanding of what you're looking at. And perhaps to be able to categorize an input, you need some high frequency component to be able to, for example, tell apart the face from a ball, for instance. Without high frequency, probably you will not be able to tell the difference. So therefore, if the perception happens, perhaps the coarse understanding of what you're looking at happens until 200 milliseconds, then you should be able to have at least some access to high spatial frequency. And that access might be minimal. And that probably might be reflected on the response amplitudes. As you can see, low spatial frequency response amplitude is really higher compared to high spatial frequency. But then our results start aligning with the literature. The low spatial frequency starts prioritized, and dominate just due to probably the luminous information picked up by the brain, and then start filling in by the high spatial frequency. Because I think the high spatial frequency needed to be, the low spatial frequency needed to be guided by high spatial frequency, which probably happens after 200 milliseconds for a better perception of what you're looking at. But I think this might be due to evolution helping humans to make a quick judgment what they're looking at the very early stages of perception. And that might be due to high spatial frequency processing.
It could maybe be testable. So if you had a task, in spaces versus objects, which probably isn't what you want to do here from the show, but you had a task like that. If that's what's happening before 200 milliseconds, you might see a differentiation among the two categories as to how high the activation is. Whereas if it's happening at 400, you see the differentiation there.
I
So you
see.
can kind of tease apart perhaps what is happening in phase one versus phase two.
And also, I also thought that perhaps I can play with the stimulation duration rather than like 300 milliseconds. I can basically, start decreasing that stimulation duration to make sure like high or low spatial frequencies process earlier, or like at specific time points.
Oh, but why would the amount of time you're presenting the stimulus make it?
So the stimulus is static, right? So, but the brain is basically processing information over time. So you can think of the stimulus as 300 copies of the same image appearing in 1 millisecond each. If you basically reduce that time, that kind of corresponds to looking at static image for less number of static images rather than more. So that can allow you, for example, to like if you've got only 1 millisecond stimulation, you wouldn't be able to see these processing orders or patterns compared to 300 millisecond version. So therefore, playing with that duration, the time duration of the stimulation, perhaps can help us understand the processing order. For example, you would not allow the brain to understand the details of the face or objects because you don't have enough time to explore. So therefore, you force the brain to maybe focus on more low spatial frequency rather than high spatial.
Explore, talk about moving your eyes to look at different parts of it.
Right. Yeah. Even in 300 milliseconds, I'm not sure if it's possible to move your eyes and explore, but the available high spatial frequency, by playing with the stimulation duration, you can probably limit the high spatial frequency access or low spatial frequency access.
So that's given that you're showing all three versions of the stimuli at that length. Right? If you show if you're telling to tell is it a face or a ball, and you show the high frequency or the low frequency or the full frequency, and you reduce the time so they don't have the time. If you only give the high frequency,
No.
they don't have the time to get to it.
Or you can even have two phases, low spatial component of one phase and high spatial component of another phase, superimpose them, and then show it for 50 milliseconds. Then it'll, if somebody recognized the first or second phase, you would know which one is processed faster.
It would be interesting to me to know if peripheral vision fell into the low spatial frequency bucket, because that could also tell us more as to why there might be two different processing, because you're going like I can see Yuri in my periphery and then look over it and there's a swap there and then I have a new thing in my peripheral. So it could be that we always are seeing high spatial and low spatial if we have normal acuity in general. And it could be that maybe there's a reason why we need two different types of processing and why it's coming from different,
So in our
Characterize.
experiment, we focused on, of course, foveal vision.
Yeah.
Um,
Which makes sense, that's where you should start.
yeah, but it's a good idea.
That could be probably, at least correlation, as to why we might be seeing things go through different pathways, because we need to continuously process so many different things at one time that we need different processes and pathways.
Is there a significant difference between a peripheral version of a stimulus versus an equally low resolution version of the stimulus?
Yeah, so the ventral pathway, the recognition region, that is believed to get input mostly from the central about 30 degrees of the visual field. And the whole field stimulation is more the foveal, the dorsal stream. So to the extent that recognition is being done primarily by the ventral stream, stimuli that are presented in the periphery are going to be less well recognized than equally degraded stimuli presented at the same time.
And what's the minimum length? That if you just show it for 1 millisecond, does
About
it
20 milliseconds,
have to be
one frame,
20 minutes?
yeah, 16 to 20.
Okay. And if you just show it for 20 milliseconds and then you stop
have
and
to
then
mask it.
incline,
You have to mask it. So show the image and then have some meaningless texture that immediately follows, so that you can't just rely on an after image or the persistence of vision to help you along. So those textoscopic presentations show the image for say 16 milliseconds, have the texture following it, and that limits the time that you have available for processing.
okay, but if that's only 20 milliseconds or 16 milliseconds, how does that thing that mask, if we say that there's the P100 tick, right? So what would happen at the 100 millisecond? Would it be affected also by the mask?
Yeah, so you had one stimulus that is proceeding down the visual pathway. It's going to elicit the P100, but soon after it's elicited the P100, the second stimulus, the mask, is going to come in and elicit its own P100.
But then, I mean, what does happen to the memory? How is the memory is involved in the processing? Like, is there any footprints that are due to the previous stimulation that are recorded in the memory and affecting the next P100 of the stimulation, or is it just blocked by the brain and you still see clear P100 for the next stimulation?
I'm not certain, but the idea of masking is that you essentially obliterate the impact of the first stimulus,
Including the memory.
So another way of getting at this might be TMS. You show the stimulus and then you block brain activity post, say, 200 milliseconds after the presentation. And then you ask, during those first 200 milliseconds, if the processing could only get to the high frequency processing, what is the person's response about what that image was? So you don't mess at the level of the stimulus, but rather you mess at the level of the brain.
I see. Right. Very good ideas. Eliminating.
Another one is coming.
I'm curious for these low and high spatial frequency DAPs. Did you control for the luminance? Because lowering the frequency or blurring it is going to decrease the overall.
Did we? That's just
We did.
we did not probably didn't.
So it could be
Fulford effect kind of thing.
Fulford.
So. So if you put like a tint, let's say one eye versus the other eye, you actually slow down the visual signal and effectively lower the contrast or the luminance, which is more the contrast, or is it the luminance? No, it's more the luminance. Lower the luminance.
Yeah.
And so this version goes slower than the other one. And with the Fulford effect is if you do that, you actually, with a moving image, get a 3D perception because it's kind of mimicking getting different perspectives in a way that stereoscopic copper glasses would do.
Cool.
I was actually reading a paper recently that looked at patients with optic neuritis in one eye. So optic neuritis is a demyelination of the optic nerve in one eye. So it slows down the signals getting to the eye, but not with a filter, but an actual brain. And they experience the Fulbright effect.
Oh, wow.
And the pendulums just.
Oh, yeah, the
consider
pendulum.
the disease state.
Wow.
Do they feel that it was worth getting the option right?
How did I get through IRB? So that could be a test for optic, right? Well,
That would be cool.
we're differentiating quite well. But
Unilateral optic neuritis.
Very specific.
Now we know what T-shirt to get, Charlie. Do you want me to test you for unilateral optic neuritis?
Very difficult.
Please say yes. Any other question? Sure.
Thank you very much.
Thank you.
Thank
Sure.
you very
Very
much.
much. Sure. Thank you, Mikhail. Well, another thing that Shoaib did